the CLIP model, which has been proposed to train actually for text and image alignment. It has been pre-trained on a large set of image caption pairs and is basically the basis for many vision language models we are using nowadays. The nice thing is that it actually allows to do stuff like image classification just from scratch and without having training data, by just defining the classes we're interested in. Here, plane, car, dog, bird at inference time, artificially create a caption from it, a photo of a plane, a photo of a car, and so on, and then just query the model to which image, the image has the best alignment, and then we have our classification. So this is really nice, and many people thought, okay, we have this large pre-trained model, and we can train it even better on more data, make the text embedding better, and solve basically everything in an open world setting. And yes, this is working to some extent. We tested it on a data set that is coming from a different project of ours. These are partly natural data. It's definitely data that can occur on the internet. It's data that people have posted on social media related to the hashtag of climate change. So we're interested in analyzing discourse on social media with respect to this topic in this project. And we wondered, how well does it work? Like, how well does it transfer to more complicated class definitions there? And these are a bit the accuracies we have. Katharina, sitting here in the audience, has produced them. On categories that are now not dogs and cats anymore, but biodiversity loss, COVID and general health, drought, floods, or wildfires. The classification rates, this is still substantial, but it goes down to a limit where you think, there is still room for improvement again. And obviously the domain shift is also strong. However, what it tells us is that we should actually still keep working on the basics of making models robust, reliable, transparent, so that we can understand why it fails here. Another example is this nice polar bear here. We're asking CLIP. It's actually pretty sure that this is a seal and not a polar bear. Why? Obviously, we don't know for sure, but my best guess is that the nose of the bear might remind of a seal, and also maybe the model looks at the pattern in the water more than at what is actually shown. These problems arise in like large models we have nowadays. They have been arising before. It's fundamental problems. We still need to look at them. It's like not gone as a problem. It's still very relevant. I want to go into the more technical part now and describe a bit on how we can measure it. So this is not yet a work of ours, just introducing the idea of generalization and robustness. So basically the problem itself has been approached from different perspectives, and one is the question of how can we measure that models are robust in practice. And when we start from a classification task, say we have an image like this, and we have a model that is trained to classify this as, for example, a goldfinch. And here the model is not even particularly confident about the decision, but that's the class. Now, one thing we can do is add corruptions to the data to push them out of domain and see whether the model can still predict right. And this is a test we can always do. It covers some interesting cases, but it can also be confusing in the sense that we never know what models have been trained on. So they can have seen exactly these corruptions at training time. Usually when we do the evaluation, we make sure that it's not the case, but we cannot be 100% sure this works properly. So this is one thing we can do. What has also been proposed is to look at worst case corruptions, which have been proposed under the term adversarial corruptions as well. So they allow us to evaluate what happens in the worst case by adding hardly perceivable input perturbations. And highly perceivable means technically within the epsilon ball of the input. So they would flip the label. So basically we have two sets of data, and the perturbations are optimized such as to push the point over the nearest decision boundary. So at least that's the goal of what they want to do. It doesn't always work, but this is the goal. And in this context, I want to, just for practical reasons, because they are very relevant in practice, highlight that obviously there are different perturbation budgets in terms of the cost of generating the attack. For training purposes, people like to use single-step attacks because they are fast, and at training time we need to be fast. So FGSM is an attack that has been relevant there. At evaluation time, most of the time we're using either PGD-based attacks or multi-step ensembles over different PGD attacks, maybe also black box attacks added. Auto attack is one such example, an ensemble of several types of PGD attacks optimized according to different losses, and also including one black box attack that makes sure that the models cannot leak gradients or obfuscate gradients. This is, of course, most expensive, but with this ensemble, if we test according to this, we can be pretty sure. PGD, again, multi-step optimization already works quite well. Sorry, wrong direction. Now, you can have a closer look. So we have the input image, we have the model that predicts something, and now a perturbation such as PGD would do it, optimizes this delta here that maximizes the loss of the model with respect to the ground truth label. And the delta is epsilon bounded, so the perturbation is smaller than a predefined magnitude to make it small. That's the established thing to do. And this is how we can practically imagine. So basically for every point in the image, we now have like some perturbation when it's added. The resulting image basically looks the same, but the classification now would be predicting a spider web with high confidence. In like the projected gradient descent method, this data is added not only once, but we are optimizing several times, like several steps, to make even stronger, stronger perturbations. And after every step, we are projecting back onto the epsilon ball to get there. So it's basically on a high level as simple as that, right? So you do one step of attacking, add some perturbation, project back onto the epsilon ball, do another step, such that with several steps you make sure that you can flip almost all samples. This works quite well, and it's also relevant. So you can look at this example here, which is just making fun, but showing that for practical applications, this is actually highly relevant, right? So you can build invisibility cloaks. There's also patch attacks that have been disturbing traffic sign recognition systems. You just put a patch and the traffic sign is gone. So these things should not happen. We have to be robust against such perturbations. I want to show a second motivation of why I think this is interesting to look at, which is a study we did in terms of model calibration. So here we just looked at at a large data set of models that have been trained in two ways, in adversarial training and with non-adversarial training, and measured their calibration properties. And actually what we see is a strong benefit in terms of calibration. So the models that are not trained adversarially are much more overconfident in all predictions. So every bar here is a model trained once adversarially, the orange one, and non-adversarially. And basically there is a strong correlation between model robustness and lower overconfidence So this is something that we would get as a side benefit, so to say. It's good to have. One issue is that whatever I showed so far works well for image classification. It's maybe not the only task we're interested in. And one contribution I want to briefly present is a paper that went under the title COS-PGD, which proposes a version of PGD, like a white box adversarial attack, for pixel-wise prediction tasks, like segmentation, optical flow, any pixel-wise regression task or classification task. So tasks like this, you have the input, you have a model, and it predicts not there is a goldfinch, but it predicts the goldfinch is exactly located here, and there is also a branch underneath, and these are the pixels that belong. Now, if we apply PGD to this task, we could basically do this. We still have the data that is optimized to maximize the loss. Now, the loss is evaluated over all pixels of the image. So we are basically averaging the gradient that we're computing the gradient of the average loss for all pixels here. So this basically gives up the location of where the loss came from, but will do something reasonable. So it basically would lose the spatial property, but otherwise could in principle work. COS-PGD is arguing that this is, however, an issue because it will only push, basically push a single pixel decision arbitrarily far away, since we are training with cross-entropy loss. Loss can always increase without making a decision more wrong, while most of the image can actually still be perfectly well classified. So what we are proposing is to add a weighing here, which makes sure that we are checking for the alignment of the prediction before computing the gradient. So that the gradient with respect to which we are doing the updates goes to the direction such that for all pixels on average, we are getting a wrong decision. And this is basically what is happening here. So the alignment is tested via the cosine similarity of the prediction and the ground truth label. And since it's a cosine similarity, it also works for regression tasks. Okay, so what does it help? If we now evaluate COS-PGD on the Pascal VOC segmentation task, then PGD will just flip many pixels to a single label, but for example, this box here will still remain the same, so will still be correctly segmented. There is a competitor, SegPGD, which basically does a binary partitioning in what is correct or non-correct, but still cannot address the issue. COS-PGD will also flip the labels in these regions here, so it will make sure that all pixels are incorrectly classified. It's also more stable than previous methods in terms of optimization. So the optimization is much smoother, which you can see here. So for different epsilon budgets, you see that the IOU for COS-PGD decreases much faster with the attack iterations. So much fewer attack iterations are needed to evaluate a method. So it's much more efficient in that sense. And with that, we can obviously also use it for adversarial training. It's more efficient, so training becomes better. And this is what you get when you train with COS-PGD versus the strongest competitor, SegPGD. Now, after COS-PGD or SegPGD attack, the COS-PGD trained model still preserves most of the pixel labels now correctly. So it works well as a trainer, while SegPGD fails. And obviously, paper has numbers about this, which I spare you mostly, but basically the simple reweighing scheme helps to make this much more efficient in practice. Now, the summary, COS-PGD increases efficiency and effectiveness for benchmarking tasks, for pixel-wise benchmarking tasks. And I've not shown these examples, but it can obviously also be applied to other pixel-wise tasks, such as optical flow or I don't know, image reconstruction if you want. Now we have a benchmarking tool, although you might not be super interested in benchmarking, but maybe you are. I want to show very briefly what we can do with it. So we used it in 2 papers as a benchmarking method. One, in order to benchmark optical flow methods for generalization ability and robustness, and in the second paper that is still under review, it's focusing on object detection and image segmentation models. We are defining reliability and generalization as 2 terms we are evaluating, where reliability uses as samples adversarially attacked data, where we don't only focus on a single method, but we optimize with COS-PGD, with SEC-PGD, with normal PGD according to different epsilon balls. So just to make sure that there is no overfitting or bias towards one of them. And in terms of generalization ability, we're using the classical image perturbations that are like added like blur or noise, as in the Hendricks paper that you saw in the beginning. First the SAD summary, which is now showing the behavior over time of like models and how models improve. So you see all models that we could basically get from GitHub, above optical flow estimation methods, below semantic segmentation methods, from 2017 to 2024 when the study was done. So the decreasing curve in IID performance indicates that here the endpoint error goes down, that's good. However, on attack data and on blurred data, for example, the errors go up over time. So actually newer models generalize worse than before. So no improvement there. For semantic segmentation, it's not as bad. So again, IID performance goes up. That is what we are expecting. So here we are looking at MIOU, up, lower, higher is better. And the reliability and generalization ability are like almost stagnating. So the curve here might look slightly pointing upwards, but the difference is between 21 and 22% on average. So not so good news there. I have some more slides on details that I will discuss at the surface, and then maybe we can discuss more about this later on. But the first finding that we could do now is check on many models how good synthetic data works in our for our purposes, and that's actually a nice finding using Hendricks corruptions and testing against actual corruptions on semantic segmentation with the ACDC dataset shows strong correlation, as you see here. Which is good. So basically, if we evaluate on synthetic corruptions, there is maybe hope that this transfers. It's not true for all corruption types, though. So it might be that for single corruption types, there is like weak correlation after all. Again, for the record, every point here is a model evaluated. So every point, full model evaluation on all categories of ACDC versus all 2D common corruptions in this case. There is influence on the backbone, and we wanted to test it here. This is a study on ADE20K that I'm showing, but again, the paper has it for also cityscapes, for example. In particular, if you look at the difference between convolutional neural networks and transformer models, you see that now transformers actually work better. So that is in line with what we expected. Like transformer-based backbones generalize slightly better. For image classification, this has been shown before. So we would assume that this happens this way. I'll show you later that it does not necessarily translate to all kind of models. What else for object detection? I'm showing here a highlight on the correlation between IID performance reliability and generalization, and in particular between IID performance and generalization, object detection models show a strong correlation. So it's, again, that's something good. I didn't expect it before. Now, for optical flow, unfortunately, what we said before about transformers does not hold anymore. So this is a rule that we think to know from classification, but unfortunately, it's not the case. So here, for example, the flow former models have a very high error rate. And now we can consider why this happens. One potential issue might be that they are maybe not trained with enough diverse training samples, but this is hypothesizing now. So the next step would be diagnosis, right? Like understanding why this behaves so differently. Is it in, for example, cost volume computations that are, again, very different, or is it really on the training data side? Both could be true. And then another thing for optical flow that I found a bit sad to see, the number of parameters does not correlate with robustness or generalization ability. Across all metrics, there is basically no correlation between the number of parameters. So training larger optical flow models, the way we are currently training them, does not help to generalize better. Again, like both together might be an indicator that there is something off with the training scheme. Okay, so I summarized a bit the takeaways we had from these two studies. I know that this was dense, but I also have some other things that I want to show. So I found it important to see that established rules that we learned from image classification don't necessarily translate to pixel-wise tasks. For example, bigger models are more robust, cannot be confirmed, and self-attention helps is also not always true. And admittedly, there are many confounding factors that are relevant for benchmarking, such as the number of training samples we have at hand. So there might actually be things that we can fix to get the benefit out of model scaling again, and basically repair this issue. Now assume that we have trained models that are robust and adversarially robust. What problems can arise? One thing that we noticed is that we also need to look at how this impacts fairness. And this is what we did in this work that I'm briefly presenting now. Starting with the observation that if you have clean training, you might get an overall accuracy on clean samples of above 90%. This is for SciFar, so this is a reasonable number. But on adversarial samples, the model just gives you 0% accuracy. Now, if you do adversarial training, the clean accuracy drops by 10%. However, the adversarial accuracy increases by 40%, which is good. Now, if we, however, check what happens to the statistics, SciFar 10 has 10 classes. The worst class after clean training still has 79%. So this is worse than the average, but not disastrously bad. Adversarial samples, everything is 0. So this is totally fair. Of course, not what we want, but totally fair. After adversarial training, the weakest class drops to 67%. So not so good a number anymore. However, what is really bad is that the relative drop for adversarial samples after having adversarially trained, the worst class is by 15% lower than other classes. So that's significant, right? So it means that from these, what did we say, 46%, this goes down to 30% or so. So it's really not a good number. What we propose in FAIR-TAT is to make the training a bit more balanced by selecting the targets appropriately. So classical adversarial training optimized this objective that you saw before, where we are adding like a perturbation that maximizes the loss of the model with respect to its actual ground truth class. This is like a one versus all training scheme. We want to delineate all samples equally far away. What we propose to do in FAIR-TED is to actually use a targeted training, which means that we are minimizing the loss with respect to a target class, making it a one versus one problem. So we are now addressing the definition of the decision boundary between two classes, and we are sampling the target class such as to overrepresent the false positive class for our source sample, so that we can basically see for which two classes do we need to redefine the decision boundary best, and then this is what the training focuses on. And by doing so, there is a significant increase in the worst class accuracy, which is obviously what we want to see. Okay, so summary, basically, be aware that vanilla adversarial training reinforces class-wise discrepancies and biases, and with targeted adversarial training and careful sampling of the targets, we can mitigate this to some extent. To be fair, even after doing so, there is still a discrepancy, right? So we are not able to fix the entire issue. It also costs something in terms of overall robustness, if I am to specify the trade-offs here, but still, in the end, we can use this tool to basically define class boundaries better. Okay, then I'm slowly transferring or transiting to interpretability. And in this context, I want to first highlight the importance of sparsity. And this is now a general work that is not in particular focused on explainability, but addresses the properties of softmax, which is highly relevant in self-attention models. So it's an operation that is happening within every self-attention operation in a transformer model. It's also usually happening at the output of all classification models. What you see here in these lines is the output of the softmax function for these inputs here. So we're drawing like we have the input 10, 10, 1, which minus 1, which we would expect to be mapped onto this point. Now, as we're increasing the temperature in softmax, this is diluting more and more towards the middle of the triangle. So basically distributing the attention more. Now, an issue with softmax is if we have like an input of 10, 6 minus 1, this like will, with temperature 0, be here, like very, very near to the point 1, 0, 0, although the second highest value was significant, right? So there should have been some value, none left. Now, if we think we can fix this by increasing the temperature, then yeah, I mean to some extent, but it's following this path here. So we're diluting a lot. We are adding a lot of attribution to this last, or a lot of attention to this last value that should have none. And this is what we wanted to address in the multi-max approach, which produces these outputs that you see here. So arguably, they're not like equally distributed, which would be like uniformly distributed, which would be even better. But it is basically a way of learning to map the softmax onto, like to stay on this axis, to remain sparse in the dimension where we want sparsity, which is the, so we want to stay on this axis, and to still be multimodal potentially and preserve the two elements that are active. How is it done? Basically, we are transforming the input to the softmax. So instead of just putting xi here, we have sigma of xi, which is the original x, plus a piecewise function computed from it. And the parameters that tell us this piecewise function are learned in the model. So what you saw before is multimax with learned parameters when training a deep transformer model. So actually, the functions that come out of this are pretty simple to parse. The equation might not look like, if you look at it for a moment, you see that it's actually pretty simple. So you have these parameters that tell you how much, like how long the segments are, and then how much the slope is at the input. Can we measure the benefit in more than like this nice figure at the beginning? We thought of two measures. One is how can we measure sparsity? So here the sparsity measure that we have tells us how many values would be near the minimum value of the attention. The multimodality will measure how many values would be near the maximum value. And we can plot it and see that, multimax always is here at 1 or near 1 with sparsity, and shows like increase in multimodality when adding, like when having the inputs that you saw before. And we can also measure then obviously what it does if we use this activation in deep transformer models, where in terms of accuracy you see an increase, small increase, but consistent increase, as we showed over several tasks. More interesting, you can actually see it in the attributions that we get. So above this would be the attribution of the model with softmax. Below, this is multimax. So it's much cleaner, you get less background attributions, it's better interpretable. So models benefit from sparse and multimodal self-attention. This is one thing we saw here. And we also measured, which I didn't show for time reasons, that there is benefit in self-attention as well as in softmax output, so for sampling itself. Yeah, and nice effect. We did not need to train for the models to become sparse, but the models actually tend to learn sparse attributions when given the chance to do so. So this was nice to see. And with that in mind, we looked at like ways of transferring this explicitly to other models. In particular, we proposed AIM, which is like a way of doing self-supervised masking of features in models, where the motivation of the self-supervised masking can, for example, be drawn from the so-called waterbirds dataset. It's an artificial dataset that has been proposed to investigate the trade-off between model attributions and spurious correlations. So basically, we have on the one hand training data, which is land birds on land and water birds on water. And at inference time, the land birds are shown on water and the water birds are shown on land background. If the model has learned to look at the bird, it will never make a mistake. If the model has learned a spurious correlation and classifies the bird by its background, it will make like a large number of mistakes. And yeah, so these would be the input images: land bird on water, water bird on land. Now ConvNext Tiny is a large convolutional neural network without like any further instructions. Actually focuses on the backgrounds here a lot. So this is exactly what you don't want to see. The method we proposed, AIM, has learned to focus on the birds themselves. And again, we're not using masks while training time. So it's a self-supervised masking mechanism that focuses, that lets the model focus on the task-relevant object without extra annotation. And this way we can ensure inherently interpretable decisions. First, what are we doing? Basically, this would be a standard procedure. We have the input image. It's going through several blocks, for example, of ConvNext encoder, and eventually we have an output. Now, in AIM, we are basically adding a top-down part to this model, which is as in a feature pyramid network. So we are extracting the features from all stages and put them together. So basically add them onto one another with slight transformations here, which you can have a look at in a second. It's lightweight like modules in these stages. And yeah, then do the final prediction here. The final loss is still really just only the classification loss of the model itself. The building blocks, as I said, are lightweight, so there are basically 2 ResNet blocks for predicting the mask, and one 1x1 convolution layer and one 3x3 convolution layer to like map the features in the feature pyramid network. So this does not add up too many parameters. Is it beneficial? How can we evaluate? So as I said, we were interested in looking at spurious correlations, which is why we started with these birds data sets, but then focused on the water birds part of the evaluation, and traveling birds is another data set that disentangles background from foreground annotations. The paper itself has many evaluations as well on ImageNet and hard ImageNet, if you're interested. Now let's focus on the water bird setting. Here we compare 3 stages. So there is basically a loss that tells the mask to mask something. And if this is the case, then it will actually focus on the bird and not on the background. And now what you see are the masks that are produced for these samples in every of the blocks. If we, the merging is just for visualization, so we're putting them one over another so that we see what part of the image the model has access to. And we see that as soon as the model is encouraged to produce a mask, it will actually focus on the right part. This also translates to numbers. We are evaluating here, on the one hand, the localization of the attribution in terms of what is called the energy pointing game score. So this basically measures how much of the attribution is within the region that we're looking for, in this case, the entire bird. And on the other axis, we have accuracy. So here it's accuracy. Here's the EPG score. Higher is better in both cases. And across several data sets, we see that by adding the masking in AIM, we're improving on metrics. So above, you see results for conflicts. Below, you see results for ResNet 50. So yeah, this is something we were quite happy about. As a takeaway, we found that self-guidance is actually possible with bottlenecking. So by forcing the model to mask out tokens, or in this case, features that it should not have access to. Thereby, we get model guidance and inherent interpretability through sparsity. And for example, on water birds, we are matching state-of-the-art performance with lower variance. On water birds, 100, which means that basically no land birds on water had been seen during training time. This gave state-of-the-art performance from end of last year. It does not only work for birds, though. So these are results on ImageNet, which also shows good performance. I'm mentioning bottlenecking here. And in terms of interpretability, this rings a bell for many people. We have also been looking into concept bottleneck models, which are bottlenecking in a completely different way. So here the idea is to basically use an encoder and map the latent representation onto concepts that are human interpretable, understandable. They might, for example, be given by human annotators. And then the actual classification is done from the concepts course by doing a linear probe. So this holds the promise of giving us inherently interpretable classifications by really basing the classification on the concepts course. One contribution that we did in this respect is the DCBM paper. Again, if you have many questions about this, Katharina is sitting in the audience. She's the first author. It builds on the fact that actually self-supervised CBMs, where we don't define the concepts a priori, have certain disadvantages. They require large training sets to extract the concepts, for example, using sparse autoencoders or different methods, but they use a lot of training data, where usually every image is an instance of one concept. So DNCBM is one of the example methods here, which means that we need many examples to find or to define a single concept. Also, there is no guarantee that the concept set that we trained on our large set will transfer to a new domain. So the idea that we had here is to learn many concepts from a single image so that for new data sets we can also retrain our model quickly, adapt it by adding new concepts quickly, and leverage data better. So doing so, basically, the idea is we are segmenting the input images from the training set and then use the segments to define visual concepts. Now every image is the source for many concepts potentially. And if we now classify an image, we can actually have the concepts that are much more granular than before. I'm only going to give a high-level overview on the entire architecture, but basically the below part here is the classical concept bottleneck model approach that you might or might not know. So there is a vision encoder. We are aligning the images that we're classifying with concept that we have extracted. There is linear probing and the prediction and explanation in the end. Now in DNCBM, we are first learning the concepts. This is happening here. We have a frozen segmentation model, which will give us a set of segments. And then we have a vision encoder that allows us to group these segments into clusters. So now this is how we get our concepts that we are using here now for the concept bottlenecking part. And what also works is after we have these concepts here, we can test their alignment with the text embeddings from a text encoder and name them in a post hoc fashion. So that is still possible. We can have visual concepts, we can assign human interpretable names to them in case someone wants to interact on a language level. I would argue that this is a nice to have tool. In many applications, it might not be required. Like imagine medical applications or so. The differences between the appearance of different diseases might be hard to verbalize on a concept level. Okay, like I'm showing one qualitative result here. The ground truth class for this example is Raft, and now these three concept sets are what previous methods have been extracting, like tubing, rapids, canoeing, waves, and kayaking. DNCBM overall gives us a similar performance. Here, the first element or the first concept which gives back tent does not really reflect the class so well, but then the others, at least on a visual level, have quite similar appearance. So we have an image of some waterfalls, rapids, and somehow obviously it maps the image to Niagara Falls, and here the naming is maybe slightly off, calling this Swaziland, which might be true for some of the images. found the last thing interesting, cleaners, probably referring to the visual appearance of the safety vests everyone is wearing. But overall, what it gives us is high data efficiency, so we can reduce the data needed for concept generation by 96%. The performance gap to the linear probe is comparable to other methods with 6%. Main takeaways here, we can achieve comparable accuracy to previous methods with only 50 images per class for concept generation, so much lower than previous methods. We can maintain the performance across several data sets that we tested, ImageNet, Places, CUP, Cypher, and so on. I think overall there are 7 data sets in the paper showing that this really generalizes now and can be easily adapted. It has superior out-of-distribution robustness compared to baseline methods, and dataset-specific concepts can improve fine-grained classification, right? So now we can really have dataset-specific concepts easily generated. What it cannot do is concept localization at inference time, which is a bit sad because we're doing all the segmentation at training time. So one thing we obviously wondered is whether we can also localize at inference time. And I know that there are approaches, for example, aligning at a token level to get coarse attributions. But one thing that we consider as next step is basically to build in an extra segmentation model that will allow us then to learn on a segment level, high resolution, well-defined localization as per concept. And yeah, this is now ongoing work, but already pointing towards this direction. So the idea is we want to have pixel level localization, maintain high quality, and get a spatial grounding that we can train without supervision on where the objects are. With what we learned before on masking, forcing models to become sparse actually triggers them to look at the right places in a more focused way, makes us very optimistic that it will also work here. And with that outlook, I'm also concluding. I presented 3 main directions of our research. First, I started with COS-PGD as an approach that allows us to benchmark pixel-wise prediction tasks in an efficient way. I pointed out that we need to be careful with the fairness, the consequences on model fairness when we do so. I showed you an example of targeted adversarial training that can address the issue. And last, we saw an example of self-supervised concept learning, which is possible from image-grounded segments, which helped us to adapt in a quick way to new data sets by making models interpretable in DCBM. And with that, I want to thank not only you as an audience, but also my group who did the work. And I'm happy for questions.
Margret, thanks a lot for this exciting talk with a lot of different topics that you tackled.
Hope it was not too confusing in the end.
Very, very interesting. Yeah, other questions. I have a list here.
Thank you for your talk. My question is specifically on slide 20 for the COS-PGD.
Yeah. 24.
And in particular, I'm wondering, is there some kind of smoothness thing, maybe an additional loss term on slide 20, where the equation was on slide 20?
The 24 you said, when the loss?
Yes, exactly. This is what I mean. Because I'm wondering if I just give it the goal to basically move each pixel away. I was wondering on the next slide, 21, the results that it is this smooth in the top right corner. That if I would assume there's a ground truth with 3 classes, I would assume that I don't know. I'm just wondering if there's anything that enforces this kind of smoothness, or whether, like in the right-hand side there, whether it is why it's not like switching between the pink and the red one, for example, for the class. Yeah.
I mean, both are wrong here, right? So
Yes,
in these examples, everything is wrong. So I
Yes.
think it.
Exactly. I'm just wondering why it selects one wrong class instead of the other.
But that's the issue in all of these.
Yeah.
Ultimately, I don't know. I can only hypothesize why this happens. My best guess would be that they are all optimizing in the optimization landscape of the model that we started with, and following the steepest gradient.
Yeah. So maybe one is just closer in the epsilon ball.
Closer, yeah, following the steepest gradient better. Closer, I don't even know, but. Yeah. So that's the dominant gradient direction, then this is where everyone goes, or where all the models go. And with cos BDD, since we're computing the gradient of the differently weight loss, we're changing the direction where needed.
Yeah, thank you.
Thank you for the talk. I have a question concerning the self-guidance that you showed. For these approaches, I'm always wondering how they scale with the depth of the network. I mean, ideally, we would like to apply this at the end to some like large-scale transformer networks with 30, 40 layers. And I'm wondering how this, how this might affect the method. Or,
what we have here as stages are actually downsampling stages in convnext, for example. So it's not a super deep transformer. And to be fair, transferring the way we are computing the mask here to transformers is the one thing that is not trivial.
Okay.
Because we are like kind of relying on the spatial location to be intact here, right? So we are masking out points, like masking out positions in the feature space. And now in transformers, since everything becomes permutation invariant, that's the thing where I would be least sure about. The depth is not the issue, right? So this can be deep. In the example, it already is like reasonably deep, convnext deep.
Thank you.
Yes, I also have a question to this. How do you train the mask estimator?
With the final loss.
Okay, so you train this thing with this.
Yeah. No, exactly. So basically there are these intermediate losses, but it's all classification losses, right? So we are encouraging the training, in the end we're encouraging it a bit to perform on all stages by having a classification loss at all of the intermediate outputs as well. But there is no extra supervision, and the loss is still the same. And then, the base model here would just be, so then you would just have this loss here, right? So this would be the baseline loss.
Yeah. So on this slide here, does the mask estimator act as a kind of attention mechanism?
Well, attention mechanism. Sorry. I mean, I don't think so. I mean, it really just has the power to switch, to gate, to really set weights to 0, but it cannot weigh between everything else.
No, it's an extreme way.
It's an extreme way of doing so, and it's also not queried, right? So it does not, here at the input of the mask estimator, it does not know what I will be looking for. So
by the loss function, the final one.
By the loss function, yeah. So through backpropagation. So if you want in an extreme definition of attention, maybe.
The question is just whether standard transformer could show this behavior. If you.
So whether we could use a transformer architecture for the mask estimator instead of a convolutional one would be more expensive. This is why we didn't try it.
Okay.
Why? Yeah. Why not? I think sure, it probably would even work better, right? So it could get the big picture of what belongs together. Maybe something to try.
Well, it looks like that.
Yeah,
it's a binary mask, and it's masking out things. Well,
yeah.
you won't have it most likely in a normal attention layer, but this is extreme case. But you could enforce it probably in the transformer by some other regularization thing or so. I don't know. Anyway.
Yeah, I mean, in a transformer layer, you would then force the values to go to minus infinity. Sorry, the keys to go to minus infinity.
Specific implementation was clear and very just from the effect that it has.
Yeah. If you make the attention sparse and multimodal.
I had another question on slide 67, I think is a good slide. What was the last method that you showed us?
Sorry, which number?
The last 67.
67.
That's at least what I wrote down.
Makes more sense.
Yeah, maybe 168 is even better. So I was wondering, so as far as I understand the method, you have kind of a spatial bias towards the concept, right? They should be spatially separatable because you're doing the segmentation. Have you thought about, I mean, extending this somehow to not have this bias? Because, I mean, the same area could have like multiple concepts. Let's say a cup of coffee. A cup of coffee is like coffee is a cup, it's a beverage, it's, I don't know if it's half full, it's some like positivism or whatever, like a lot of things there.
Yeah, we thought, yeah, I understand the question. So currently this is an ad hoc decision here. This could also be like some hierarchical grouping, which would make a lot of sense.
Okay, cool.
So probably in this.
Yeah. Maha?
Sorry, I didn't see. Sorry, no, just you are.
Yeah. A very basic question, but I'm interested in how to initialize this when you start optimizing for the adversarial attack. How would you initialize this?
The perturbation?
Yes.
It's usually initialized with random noise.
Without any constraint on how it relates to the original image or the statistics of the noise?
Yeah, so the noise is epsilon bounded, same way as the perturbation will be epsilon bounded.
Okay. Yeah, but
but
not
I think like
to be independent from through the optimization remains independent from the image, its original image itself.
I mean, you have the delta, but it's optimized for that image. So for the image and its label, you're doing this gradient ascent to maximize the loss. So this is how the image information comes into the perturbation.
Yes, but you are fine with coming to a point where these adversarial attacks are highly correlated with the original image itself. Yes. No problem.
I mean, in the end, people have been arguing that this is something you want. So for non-robust models, we see that this correlation does not come. And this is also let me quickly go to the very beginning. I think here you, or maybe it is, and I just cannot recognize the properties of a spider web here, so maybe, but basically here I don't see any strong correlation to the image data. And we still have a classification as spider web. There are studies that show that as a model becomes more robust, then the perturbation would actually look like the target class. So if I want to attack a model to predict a car, then the best thing the perturbation can do is add a car somewhere or hide a car somewhere. And then we're pretty close to having models that do what they're supposed to do.
Okay. Thanks a lot. Yeah. Interesting.
So I have a question regarding the AIM method.
So you said you're somehow encouraging that there should be a window it's focusing on. Can you quickly repeat how that's done and whether it's only one cluster or window that it's focusing on, or whether there's potential there for many? I think the other result shows that there are many possible.
It's a mask, right? So it just predicts for every. So what you like the resolution here is just the resolution we have at the different blocks. So block 3 means the image has been downsampled several times, which is why it's coarser. Then here it's finer, and it just predicts a mask for every position, like a mask value for every position, which can be 0 or 1. Now, what I mentioned is this we call it active area loss, which basically encourages the model to preserve only 25% of the features. So it's just saying, we're adding to the loss if more than 25% of the pixels are set to 1. If we don't do that, the model just masks something and does not learn to focus on the right things.
So there's not really, it's like a compact constraint, more like just the amount of features.
Yes.
I see. Okay, that answers my question.
Yeah, I think implicitly, since the mask predictor has a convolutional component, this is a bit where the compactness comes from. Just architectural bias.
Sure. One question to the multi-maxing idea. So, the softmax is kind of an issue for transformers because it has this quadratic scaling, right? So there's a couple of research that tries to remove this completely or try to do it faster. And I was wondering how this scales. I'm not sure because I didn't remember the formula, but is this still quadratic? Does this change something, or?
I mean, the attention is what is quadratic, right? The self-attention is what is quadratic because every key attends to every query attends to every key.
Yeah.
So that's where the quadratic behavior comes from. The softmax scaling behavior is, now let me think about it, but basically this just tells you that at every point we have to go over all n. So this is an O of n, right? So we have to compute the output for all n elements to evaluate softmax. Now, obviously, if the number of tokens is large, this is still large. And there would be, I don't know, hierarchical softmax approaches or so, sampling-based approaches that let you do this efficiently. Now, what you see here is basically the softmax equation. We're just changing the input, right? So this multimax is basically just transforming the input x to sigma of x, which is an element-wise operation. So computationally, it's not bad.
Sounds good, yeah.
I have a question also on this multimax. So I just want to clarify whether I understand correctly. So you put this now in the attention mechanism instead of the softmax.
So we are adding basically like single scalars as learnable parameters.
Yes, exactly. But the input is still basically q times keys and then divided by the square root.
That's the values, like the sum of the values weighed by the self-attention.
I'm wondering specifically because you, in the original scaled softmax attention, you divide by the square root of the head size, which is kind of as an implicit temperature scaling there. At least that's what they argue in the original paper. And I'm wondering whether this has an effect here or whether you just leave this out, this division part.
Okay. To be really fair, I need to look in the code to tell you what exactly, whether X has the normalization or not.
Yeah. I was just wondering because this is also kind of the temperature. At least
but a fixed one, right?
Yeah, it's a fixed one for the head size specifically.
Yeah. To be very fair, I don't know, but what I understand what we did here is take the input as is with the normalization, set it to X, and learn the rest on top.
I mean, it doesn't matter because it's a learnable parameter, so it could just learn to invert this, but it would be interesting to see the effect of doing it with or without the division. I would be interested in that. Yeah. Thank you.
Yeah, good point.
Okay, if there's no other question, I think we have time outside. discussion. I'd like to thank Margret again for this presentation. Thank the audience and also that don't know how many people joined online. We will share it afterwards. Last time I think with respect to the weather condition, most people avoided to travel down.
Maybe.
Enjoyed your presentation in a relaxed manner with a cold beer.
Or maybe just went swimming somewhere, which I would also understand.
Thank you.